Hello dear colleagues and students. My name is Dilshad Rajanov. I'm IB Diploma Program Physics teacher. In this video I'm going to explain Kirchhoff's laws. This lesson is designed especially for IB students, and Kirchhoff's laws are used in calculations of currents and voltages in simple circuits as well as in complex circuits. In this video I'm going to explain two laws of Kirchhoff, which are law for junction and law for loop. And I'm going to explain some examples, worked examples using Kirchhoff's laws. Hopefully this video help you to deeper understanding the concept and to apply your knowledge in future examinations and assessments. So let's start with the first law of Kirchhoff for circuits. This is called sometimes junction law. So what's a junction? Let's say this is a wire conducting electrical current, and this point can be considered junction. Let's say what's happened here. So the current coming into the junction, for example this is I1 current, is equal to the current going out of the junction. This is because of law of conservation of charge. So we can say I1 equals to I2. So again, amount of charge coming to this junction per unit time equals to amount of charge going out of the junction, because current is charge per unit time. So let's see what happens if I'm going to add more wires here. So more wires. Let's say another wire is connected to this junction, and these are no more equal because current coming into the junction will be split into two parts. So let's denote the second one is as I3. So what happens? So again, according to the law of conservation of charge, charge coming per unit time in a junction must be equal to charge going out of the junction. That's why we can write I1 equals to, this is charge, current coming in junction equals to current going out of the junction, I2 plus I3. If we move I2 and I3 to the left-hand side of equation, we get I1 minus, move to minus, I2 minus I3 equals to 0. This is the Kirchhoff's junction law, which means sum of the all currents coming into the junction equals to 0. But you need to be careful here, because as you can see, this is positive here. Okay, let me use a different color. This is positive, this is negative, and this is negative. And we add them together to get 0 according to Kirchhoff's first law. So how we can make sure that we have correct sign? It depends whether current is coming into the junction or going out of the junction. If current is going into the junction, then it's positive. Current coming into the junction is positive. Going out of the junction is negative. Let's double check. Okay, I1 is going into the junction, therefore it's positive. And I2 going out of the junction, it's negative. I3 is also going out of the junction, therefore it's negative. That's why we add them together, we get 0. So let's have a look at this example. So how we apply junction law. We have a circuit here, current going, and how many junctions we have? So junction 1, junction 2, junction 3. Let's label them. First, second, and third. And we have currents labeled, and our question is, what's the current going out at third junction, which is X? Let's work to this question together. So for the first junction, we have, remember, current going into the junction is positive, current going out of the junction is negative. So we have 3.4 going into positive, 2.1 going out, that's why it's negative, 2.1 is negative. And we have current going out of the junction. Let's label it by a different letter. Let's say it's Y. Y is going out, therefore it's negative. Y. So Kirchhoff's first law, junction law, says if the sum of all currents in junction will be equal to 0. So this all of thing will be equal to 0. Let's solve for Y. So Y is negative, that's why I'm going to move to the right hand side to get positive Y. Y equals to 3.4 minus 2.1. So 3.4 minus 2.1 is equal to 1.3 amperes. Right? Next, for second junction, so we have here Y equals to 1.3 amperes. So for second junction, we have 1.3 ampere going into the junction, therefore it's positive. 1.3 plus positive. Another 1.3 is going into the junction as well, positive 1.3. And we have current going out of the junction. Let's label it with a different letter. Let's say it's Z. Z is negative. Negative because it's going out of the junction. And all of them equals to 0. Let's solve for Z. Z equals to, Z is negative, therefore I'm going to move that to the right hand side to make it positive. Z equals to 1.3 plus 1.3, which is equal to 2.6 amperes. 2.6 amperes. So last junction, junction number 3. We have Z, which is 2.6 amperes going into the junction, positive, 2.6 is positive, and 2 amperes is negative, negative 2 amperes, because going out of the junction. And X is going out of the junction, is negative as well, equals 0. So X is negative, therefore I'm going to move the right hand side to make it positive. X equals to 2.6 minus 2.0, which is equal to 0.6 amperes. So our solution to this problem is X equals to 0.6 amperes. So this is another example of application of junction law. But in this case we have only one junction here in the middle. So we know that the current going into the junction is 3 amperes. Another current is 0.4. Current going out here is 1.4 amperes. And current going out here, 2.2 amperes. And we don't know what's the current going out here. But the sign, direction here is conventional. We don't know yet whether the current must be going into the junction here, going out of the junction. So at the end, if we have a Y negative value, which means initially we chose direction incorrectly. Let's have a look. So all currents, sum of all currents is 0. So first, positive, because it's 3 amperes is positive because going into the junction. 3.0 positive, 0.4 is positive going into the junction, plus 0.4, 1.4 is going out of the junction, that's why it's negative, 1.4, Y we say, okay, we don't know yet, but let's see, negative y, and 2.2 ampere is also negative because going out of the junction. And all of them equal to 0, equal to 0. Let's solve for y. Let's solve for y. Y is negative, therefore I'm going to move the right hand side to make it positive, and the left of the equation, left hand side becomes 3.0 plus 0.4 minus 1.4 minus 2.2. So let's calculate. 3.0 plus 0.4 is 3.4. 3.4. Negative 1.4 minus 2.2 is negative 3.6. 3.6. So 3.4 minus 3.6 is negative 0.2 amperes. So we have negative sign here, 0.2 amperes, which means we chose initially here the direction synchronically. Actually, meaning current 0.2 current must be going into the junction. This is second law of Kirchhoff for loop. So what's a loop really? Let's say we have a power supply or cell with positive and negative terminals, and these are wires, and this is a resistor R, and we have EMF here, epsilon. So how do we apply this law? So we need to choose a direction, in which direction we are going to look at the loop. Let's say we have clockwise direction, and also we need to, as the first law, we need to look at the signs. We need to be careful with signs. So we have voltages in here. Voltage here is epsilon. Voltage across this resistor is from the Ohm's law is I times R. Let me write in different color. Voltage here equals to IR. But what's the sign? So if we go clockwise, we see this is positive, this is negative, so potential drops, meaning voltage is negative. Here, voltage is negative. That's why it's negative E, negative epsilon. And if we go here, it depends what's the direction of current. Okay, current is flowing from positive to negative. Current is flowing through resistor to the right. But we're looking at this position to the left. That's why potential here is more than here. When we go from, because we are looking at clockwise, when we go from right to left, potential increases because potential here is more than here. Therefore, this is overall voltage IR is positive. I times R is positive. So we have, in this loop, we have only two components. Therefore, we just add them together to make equal to 0. So we can say epsilon electromotive force equals to IR. Let's have a look. So it doesn't matter which direction we chose. It doesn't matter. I'm going to use the same circuit to prove that. So this is our, I'm going to draw the same circuit side by side so we can see. We can see. So these are same components. This is our electromotive force. This is our resistance. Voltage across our resistance is still V equals to IR. Voltage here equals to electromotive force. So what happens if we choose anti-clockwise direction? Anti-clockwise direction. So let's label these parts. So this is positive terminal, negative terminal of cell, and current flows from positive to negative, from positive to negative. So if we look at this direction, so if we go from right to left across electromotive force, so potential from negative becomes positive, therefore potential is increasing, so voltage is positive. Voltage is positive. This is positive. And if we go across the resistor, potential here greater than here, because it's connected positive terminal, it's connected negative terminal, so potential decreases, therefore voltage is negative. This is negative, minus IR. So we have only two components. We add them together according to Kirchhoff's second law, which is loop law. It's equal to 0. So epsilon equals to IR. So it really doesn't matter which direction we choose, as long as we correctly apply the sign convention. So epsilon equals to IR, epsilon equals to IR. So in this example, we are going to apply loop rule for this given circuit. We have here electromotive force 1, the first electromotive force, is 2.0 volts, resistor 1.4 ohms, and current flowing through this loop is 0.8 amperes. Second resistor is given 2.1 ohms, and a known variable here is second electromotive force. So we need to find the second electromotive force. Electromotive force of second cell. Let's see. If we choose, for example, direction as clockwise, we need to consider signs here. So we have positive terminal, negative terminal cell, positive terminal, negative terminal cell, and current flowing in this anti-clockwise direction. So if we start from this corner, so if we go from left to right, so potential drops from positive to negative. So this we call to negative 2, negative 2.0. Because positive, negative, from positive to negative decreases. That's why it's negative. Current, next element here is resistor. Current going from the resistors is from right to left, because we know this arrow here. From right to left. That's why potential here is greater than here. That's why current always flows from point where potential is greater to point where potential is lower. That's why potential increases across this resistor if we consider it from left to right. So we have potential here is IR 1 positive. I equals to 0.8 times 1.4. Next is our second cell. If we go clockwise, so from positive to negative, so it drops. That's why it's negative. Negative epsilon 2. And here we have again current going from left to right, but we're looking from right to left. So potential here is greater than here, that's why it's flowing from left to right. It means if we go from right to left, potential increases, which means voltage here is positive. Plus I 0.8 times 2.1 equals, so we added all voltages, equals to 0. So let's solve for epsilon 2. So epsilon 2 is negative, that's why if I move it to right hand side it becomes positive. So we can solve for epsilon 2. Epsilon 2 is positive, equals, and we are left with negative 2.0 plus 0.8 times 1.4 plus 0.8 times 2.1. So let's try to solve this. Epsilon 2 is equal to minus 2.0. So we can factor out 0.8. 0.8 plus 0.8 in parentheses 1.4 plus 2.1. If we continue to solve this, epsilon 2 equal to minus 2.0 plus 0.8. So if we add 1.4 plus 2.1, we get 3.5. So if we multiply 0.8 times 3.5, what do we have? So if we multiply them together, we have 2.8. 2.8. So epsilon 2 equals to negative 2.0 plus 2.8, which is equal to 0.8. Unit of electromotive force is volts. So answer is 0.8 volt. Epsilon 2 equals to 0.8 volts. In this example, we are given the circuit. Here, electromotive force is 6 volts and 2 resistors in series, 10 ohm and 2 ohm, 10 ohm and 20 ohm respectively. And we are asked to find what's the current along this circuit. So we need to apply Kirchhoff's second law to find the value of I. So I go for clockwise because it's convenient for me. You may also consider going anti-clockwise, but remember, it doesn't matter which way you choose, as long as you choose the signs properly. So this terminal, if we start from this part, this terminal is positive, it's negative, battery. So if you go from down, so remember clockwise, from this part to this part, from negative to positive, potential increases. That's why we have positive 6.0. We go from across the resistor. So potential here is greater than here, therefore current flows from left to right. That's why potential decreases here. We have negative. Ohm's law is I times 10 times 10. And here current flows also from up to down, from positive to negative. That's why potential drops, negative. Minus I times 20. All of them equal to 0. So we need to isolate the members which has I to solve for I. 6 equals to, let's rewrite it in a different way. 10I plus 20I. So 6.0 equals to 30I. So current equals to 6.0, 2 significant figures. We want to keep the number of significant figures appropriately, divided by 30. So let's see, I equals to 6 divided by 3 is 2, 6 divided by 30 is 0.2. But we have 2 significant figures here, that's why I'm going to add one more significant figure to make one more 0 to make 2 significant figures. So current flowing in this circuit is equal to 0.20 amperes. In this example, we're going to look at this circuit. This is quite complex circuit. We're going to use both laws of Kirchhoff to solve for currents flowing the resistors. We're given 2 electromotive forces, 9 volt and 12 volts, and 3 resistors, 3 ohm, 2 ohm, and 6 ohm, and they are arranged as shown. Our task is to find current flowing through these resistors. Let's see. if we say that current flowing, so 9 volts is try to drive current upwards, let's say this is current I1, then here this electromotive force tries to drive current upwards as well. That's why this is a current I2 and this is I3. So meaning we have junction here, 2 currents go here and join together to make I3. So let's try to apply the Kirchhoff's laws to solve. So if we apply first law of Kirchhoff for this junction, we have current going in is positive I1, current going out is minus I3, current going here is positive plus I2 equals to 0. And we need to apply second rule of Kirchhoff because we cannot solve for anything here. We don't know. Second law of Kirchhoff for loops. Let's say this is the first loop and this is second loop. If we look at these loops, we have, okay, 1, 2, 3 components. If going from down to up, so potential increases from negative to positive, that's why it's positive. 9. So potential difference here. Current flows from point where potential is greater to point where potential is lower. That's why it's negative. Potential drops. 3 minus 3I1. 3I1. And here again, current flows downwards, potential drops, therefore it's negative. Negative 6I3. All of them equal to 0. For second loop, we have potential, if we look at from this side, current flows downwards, meaning potential here is greater than here. That's why this part is positive. 6, which is resistor, times current, which is voltage. I3 positive. Current goes this way, and here is we have plus again. Potential drops to the left. That's why, but we are looking from left to right. That's why it's positive. 2I2, and here we have positive terminal, negative terminal. Going from positive to negative is decreasing, therefore it's negative. Negative 12 equals to 0. So we have 3 equations. We need to solve the system of equations to find currents. We have 3 equations and 3 unknowns, unknown quantities. Let's see what we can do here. So let's get rid of the zeros. So make a quick equation so we can use them better. So I1 here, for example, from this first equation equals to I3 minus I2. And from this equation, we can say that 9 equals to 3I1 plus 6I3. And from third equation, we can say 12 equals to 6I3 plus 2I2. So we more or less simplified our equations. So if we substitute I1 here, we get rid of the one very unknown. So if I'm going to substitute I1 to first equation, 9 equals to, so 3 times I1, meaning 3 times I3 minus I2. So 3I3 minus 3I2. 3I3 minus 3I2. So we have here, and we have 6I3. So we have 2 same members. So 6 plus 6I3 plus, 3I3 plus 6I3 is 9. So 9 equals to 9I3 minus 3I2. And we have second equation here. We are left with these two equations. This equation here and this equation here. Let's see, how can we manipulate these equations to solve for unknowns? So this equation is divisible by 3, and this equation is divisible, so 3, 9 divided by 3, 9, yes, divisible by, this equation is divisible by 2. So we can isolate I2s in both cases. So let's divide this equation by 3. Divide by 3. So we have 3 equals to 3i3 minus I2. If we divide this equation by 2, we have 6 equals to 3i3 plus I2. Okay, we more or less simplified our equations. So we have I2 equals to here I2 and I2. So we can find I2 from this, both equations, and make them equal. From the here, I2 equals to, this is negative, that's why I'm going to the left, I'm going to move to the right. That's why 3i3 minus 3. What's I2 here? Is 6 minus 3i3. 6i3. So I2 here, they're same, that's why we can manipulate it. 3i3 minus 3 equals 6 minus 3i3. So if I'm going to manipulate this further, we can move unknowns to one side of equation and just numbers to one side, another side of the equation. So 3 minus 3 becomes positive, that's why 6i3 equals to negative 3 moved to the right becomes 9. So therefore I3 equals to 9 divided by 6. 9 divided by 6 is 1.5 amperes. So I3 here is 1.5 amperes. Okay, let's see if we can find different variables here. So we here, let's see our one of some last equations. So we have I3 here. We found I3 to be 1.5. That's why we can substitute here to find I2. So I2 equals to 3 times I3 is 1.5. 1.5 minus 3. 3 times 1.5 is 4.5. Minus 3 is also 1.5 amperes. So I2 equals to also 1.5 amperes. So we have this equation right here to find I, or this equation here. So I3 equals to 1.5 amperes. I2 equals also 1.5 amperes. Therefore, I1 equals to 0. I1 equals to 0. So far, we have looked at the Kirchhoff's laws and looked at some problems solving problems using Kirchhoff's laws. Let's just revise. What's Kirchhoff's laws? We have two laws of Kirchhoff. First law is law for currents, or law for junction, and second law is law for voltage, or law for loop. Right. So it states that Kirchhoff's laws, first law states that summation of currents coming into the junction equals to 0, but we need to have sign convention that if current is going into the junction is positive, current going out of the junction is negative. And same sign convention, similar sign convention, it can be used for loop. So if potential decreases over the element of loop, then voltage positive. If potential decreases over element of loop, then potential is negative. Okay, so let's just have a look at examples using the simulation. Okay, I can take wire, resistor, battery. So we can model these laws using the simulation provided by FET website. So let's take a battery. These dots represent electrons. So I can take a resistor and connect the resistor with wire. So we can see how current moves. But I just hide electrons for the sake of clearance, so we don't be distracted with electrons. Just focus on current, because we can measure using a meter we can measure current or voltage using voltmeter. So, and we can also see what's the voltage in the battery and what's the resistance in the resistor. For example, this is 10 ohm. So let's just have a junction to demonstrate Kirchhoff's first law. Okay, so I have here, I need to create a junction, so at least 3 wires connecting to a point. Okay, right now I have here 3 wires connecting the same point, and I need to do the same thing with the opposite side, so I can make a circuit complete. Okay, so, and I need the ammeter to measure voltage. Sorry, not voltage, current. So current going out of battery is 1.8 amperes. Meaning current coming into this junction, let's consider this junction. Current coming in this junction is 1.8 amperes, meaning this is positive because it's coming into the junction. It's 1.8 amperes. Sorry, switch language. Yes, 1.8 amperes. It's positive. Then we need to measure current going out of junction, this direction and this direction. Therefore, I need 2 more ammeters here. So 1 ammeter here. And 1 more ammeter here. So, I cannot read, now I can read the meter. So current, because it's positive terminal, current is flowing from positive to negative terminal of battery. So current coming into this junction is 1.8, since that's why it's positive. Current going out of the junction is 0.9, therefore it's negative 0.9 amperes. And another current going out of the junction is also negative because it's going out of the junction, so negative 0.9 amperes. So all of this should be equal to 0 according to first law. So let's check. 1.8 ampere minus 0.9 ampere minus 0.9 ampere. Yes, that checks out. Let's have a look at another example using loop. Perhaps I can use this same circuit because we have 2 loops to have a look at an example with this second law of Kirchhoff. So I have here 1 voltage, 1 component and second component. So potential, the sum of voltages here must be equal to 0 according to second law of Kirchhoff. Let's have a look. So this is negative terminal of battery, this is positive terminal of battery. That's why current flowing from positive to negative, meaning current flows from point where potential is higher to a point where potential is lower. That's why potential decreases when we go from left to right. Let's have a look. Consider situations when we go loop in clockwise. So I can start from this battery here, the cell. So if I'm going to from right hand side to left hand side of battery, from negative to positive potential increases, therefore I can say that voltage here is positive 9. So voltage is 9 volts positive. And we go here, current is flowing from left to right in this resistor. Therefore, potential decreases because current flows from point where potential is higher here and lower here. Therefore, current is flowing. That's why potential decreases. What's the potential here? It's literally V equals to IR. So we have here current equals to 0.9 times resistance. Let's have a look. Resistance is 10 ohm. So sorry, I have mistake here because I should have here the negative sign because potential drops, meaning voltage is negative. So 9 volts minus 0.9 times 10 is also 9. It equals to 0. So it also checks out. In the same way, we can look at this loop, upper loop. So current flowing from left to right here, from left to right here. Let's have a look at this loop. Let's start from this part here. Okay. Here, potential decreases from left to right. That's why if we go from left to right, voltage is negative. Resistance is 10. Resistance is 10 volt. Okay, just not the right units because in all numbers we have SI units. And current is 0.9. 0.9 is negative. Then if we go here, so from right to left, current is flowing from left to right, but we go from right to left because we're looking at clockwise. So going from right to left, potential increases because current is flowing to the right. Therefore, it's positive. I equals to 0.9, resistance equals to 10. So it's 10 times 0.9 equals 0. So let's check. Minus 9 plus 9 equals to 0. It's also checks out. So we just using simulation looked at how Kirchhoff's laws can work in real circuits. I hope this video was useful and you enjoyed watching. And hopefully in the future you can apply knowledge learned today to use Kirchhoff's laws in all circuits. Thanks for watching.